All right. First thing we're going to do is go through test 3 from November 17th, 2016. This is the first version. Make sure everything is right. All right. Standard rule set. I did not put it on this copy, but we will be using this reference figure and some of the multiple choice. All right. When we get to them, I'll put them up. So we see here a copy of all the equations and stuff that we'll need. If anything else comes up that we need, I'll put it up on the whiteboard on Thursday. Two strings, identical length, material, and tension, both resonate at the first harmonic. One string is thick, the other string is thin. The thinner string has what? Higher frequency. Tension of a string has what units? Newtons. Hooke's law in vector form is E. The units of pressure are, now it's not B, it is E, newtons per meter squared. Newtons per meter squared can be converted into atmospheres. It's not atmospheres per square meter. Now, of these strings, which one is vibrating at its second overtone? String 4. Yes. The velocity of sound in a vibrating string is D. Tension divided by linear mass density. String vibrates at its third overtone. How many antinodes are there? So, which string of the 5 has is the third overtone? So it's string 2. Fundamental frequency, first overtone, second overtone, third overtone. How many antinodes are there? There are 4. Which one of these is heard, or is the frequency of sound heard by a moving source towards an observer? It is not B. So moving source means that the parentheses are in the numerator. And if it's moving towards, it has to be a bigger number. So which one of these two produces a bigger number? It's D, or it's E. Pendulum, a spring pendulum has a period of 2 seconds. You quadruple the mass. The new period is
4 seconds.
4 seconds, yes, let's talk about that. Period is 2 pi m over k. If you quadruple the mass, you're going to get a bigger period. So that eliminates C, B, and D. Now it's only A and E. If you quadruple the mass, you introduce a factor of 4. Square root of 4 is 2. Yes?
Can you explain number 8 when you're done?
Okay. So for number 8, we're looking for a moving, I'm sorry, I am wrong. It is not E. E is what? It's that's the moving observer equation. So basically I I said, I looked at a source, never mind. So it has to be B. So source, it is early. It's, the parentheses is in the numerator. Oh God, it's not in the numerator, it's in the denominator. The moving observer is in the numerator. And actually, I'm going to write this down just so I have this. Probably the thing that I would do is I would just write this stuff down right at the start of the test and then do it that way. So that's all that I need. String 2 is vibrating at, now these may not, let's see, string 2, yeah, there is a correct answer for string 2. Which harmonic? It's going to be E, fourth harmonic. This is first, second, third, fourth, and fifth. Now, this is the fundamental frequency. This is the first overtone, second overtone, third overtone, fourth overtone. Which string has 3 antinodes? Four. String 4. You measure the period of a simple pendulum. It's 3 seconds. You increase the mass. Which one is the new period? B. Simple pendulums are not spring or not mass dependent. Which string only has 2 nodes? So it's E. What's the inverse of frequency? Period. The units provided by 1/2 rho v squared without any conversions is what? So this is preparing you for a Bernoulli's equation problem. So 1/2 rho v squared gives you what in units? Well, you could just figure it out. Rho, kilograms per meters cubed, velocity squared, meters per second squared. So what we're going to do is I'm going to cancel one of these, and I'm left with kilograms, meters, second squared. Gives me this, which leaves me with newtons meter squared. For a string, the first overtone is same as what? Second harmonic. Object is negatively buoyant. Which of the following is true? C. A spring pendulum is correct. Gravity independent. And probably you can immediately narrow it down because these two, dependent and independent. It has to be one of those. Which string is vibrating at its third overtone? So you can just look that up. Third overtone gives you string 2. Probably another good thing is when I give you these list of strings, just label them real quick, and then you can just quickly reference them. For a resonating half pipe, so we got a half pipe. The third harmonic is the same as what? B, first overtone. The harmonics go first, third, fifth. First harmonic, fundamental frequency. Third harmonic, that's the first overtone over the fundamental frequency. Lambda, not wavelength, is what? Yes. For n equals 2, for a resonating half pipe, its frequency is called what? E. Even ends do not exist for half pipes. All right, we have a moving observer away from the source. I'm reading that correctly, am I not? The observer's moving, the source is fixed, and it's moving away. So we're going to hear, it's away, so we're going to hear a lower pitch. It's a moving observer, so it has to be in the numerator. So it has to be D. This one would produce a higher value, but we need a lower value. In 24, it's still a moving source, but now it's moving towards, so we have to get a higher value with the parentheses in the numerator, so it has to be E. When n equals 3 for a vibrating string, it is vibrating at what? The third harmonic, correct. All right, and that's the first part. So as we're looking at this, we could see a few problems peek out. I like this test. This was a good test. One is, I would almost assume that these two are solid locks. One is an Atwood string. It may not be that L2 is asked for, but I could ask for anything. The other one is a Doppler shift. And I want to know what the velocity of the car is. I give it as a ratio. This means that FA is not given, and I don't ask for it. So I want to knock out these two because they're the ones that we're most familiar with. Atwood string. We have L1 is given, L2 is not given. We have a hanging mass that is given. I'm given the mass of the string. It is, and I'm given the frequency. It is at the first overtone, so N is equal to 2. So from that, all that information, I got a lot of stuff. So it's an Atwood string. Vibrating strings, F equals NV over 2 times the vibrating length. The vibrating length is that. So it's L1. The velocity is the square root of tension over linear mass density. The hanging mass provides that tension, and the tension is mhg. Lambda is the linear mass density, mass of the string divided by the total length. The total length is L1 plus L2. So this becomes mass of the string L1 plus L2. So this becomes mass hanging gravity, mass of the string L1 plus L2. And that is the velocity. So I plug that velocity into the frequency. Frequency is N over 2L1 square root MHG L1 plus L2 MS. So you got the frequency. Now we're looking for the one unknown, L2. L2 would probably be the length that I'm looking for, not L1. Mostly because L1, there are two spots of L1, and that makes the algebra just a little bit weird, I think. So I would say be able to solve for everything but L1. I will try to remember not to ask for L1. You square it. Square root drops. And the other thing that makes me just sit here and go, ugh, L1 is nasty, is that you got an L1 squared in the denominator and an L1 in the numerator, and the L1 isn't directly over the L1 squared, it's encased in the parentheses, so it can't really cancel all that well. So to get to L2, I'm going to take that and bring it up.
Do you need to square the in the 2?
Yes, thank you. That would have been bad. Also, n is unitless, so you wouldn't be able to detect it in a unit check. So that n should be squared. In fact, there's another error. Tell me where the other error is. Should be a 4. Thank you. So 4L1 squared F2 MS. One of the things about physics that I find fascinating is it is interesting for the students to get it right. I mean, I desire the students to get it right. What's really fascinating are, and yeah, I think you're asking for me to widen this up a bit. What's really more interesting are the students who make the mistake, realize they make a mistake, and then go, what do I need to do to correct it? And then answer that. And I think physics is all about making mistakes and then recovering from them. Don't think that you're by making a mistake, all of physics is disproven. It's really testing you to see how you can recover and keep going. 4L1 MS F squared over N squared MHG L1 plus L2. So this becomes 4L1 squared F squared MS N squared MHG minus L1 is equal to L2. Yeah, L1 would be a quadratic of some sort, and that would be nasty. The one thing that I would say that is possible is that I could ask for the total length L, which means that all you would have to do now is plug in these values, and that is L1 plus L2 equaling L. It doesn't matter that there is an L1 in the equation. You could just immediately solve for L. But I asked for L2, 4.2 squared 2,000 squared. Mass of the string, remember, kilograms. In 2 squared. Mass that's hanging, 1,000. G10. And that gives me this. And I think the, this is going to be, I can tell you what happened in the test. I told them that they should expect a negative number. Now, what I did is I accidentally made a mistake in picking the wrong set of numbers. The math is correct. There's nothing wrong with the math. One of the things that I like to do is go over the tests, realize what mistakes I made in that test, and then sit there and basically do kind of a mental bad professor, slap my hand, and so that something like this doesn't happen. You're gonna get a legitimate answer on this test. I just told the students, look, if you get a negative answer, that's fine. And, or what I did, I think what I could have done is, I could have just increased the mass of the string. I could have decreased the hanging mass. Could have changed a number real fast on the fly in the test. I don't recall what I did, but that's the number. In problem 3, we have, and there are the things. Problem 3, we have a car passing by a siren. So this is a moving observer. So it's a moving observer. We don't know the velocity or the source. So this is a roulette wheel style problem. What we can do is we could take the frequency heard towards and the frequency away. Frequency towards is the initial frequency, 1 plus V over Vs, F 1 minus V over Vs. Those cancel. If F towards is equal to 1.5 F away, then F towards divided by F away is equal to 1.5. And so this is the equation that we use. Bring that up. What am I looking for? I'm looking for V. Distribute get my V over Vs terms on the same side. So V over Vs, factor it out. So V is that. So this is that the velocity of sound, 1/5 of that is the velocity. So it's 350 divided by 5. So it's 70 meters per second. And that's the velocity of the object. And that's as far as I can take it. I can't ask for the frequency towards or aways because none of that, those frequencies are not given. So I can't ask for the source frequency because it's not given. All I did was give a ratio. All right, so that's problems 2 and 3. Appetizing. Now, once again, just to go into tutor mode, one is Eschenberg is weak. I can figure him out. He's so predictable. Everything. You look at these tests, one after the other. It all ends up being, I mean, he may ask for weird, different things, but it's always typically the same problems.
Can you go back to that one real quick?
Sure.
Is that 350 over G or 350?
3 over a mutant 5. Because 0.5 over 2.5 is 1 over 5. Are you ready? Okay. So he gives you that the stretch length of this spring is 10 over pi squared meters. That's a very odd number with that pi squared. That's basically him telling you that something's going to cancel and there's a pi squared that'll do it. You've got a spring and you've got oscillations. So the two equations I would immediately write down are T equals 2 pi m over k, and F is equal to kx, the magnitude of the of Hooke's law. In this particular equation, it's stretched a particular distance. So there is a kx up and there is an mg down. And what's really perplexing about this is that the mass was not given. Oh no. Sum of the forces is kx minus mg, so this becomes mg kx. So you've got this equation and you've got that equation. Let's ID what we know and don't know. I don't know the mass in any of these. I don't know the period, but we're going to figure something out from that. And oh my goodness, we don't know K, but I do know I'm on the planet Earth. Oh no, we got trouble. So we got a big mess right now. There's another equation that we need to know because we're dealing with the number of oscillations, we're dealing with period. And the final thing is I'm looking for total time. So the number of oscillations times the period. That's what I'm looking for. So So the total amount of time is what I'm looking for. It is the number of oscillations times the period. I am given in, finally, I've got something for a change. So I plug in period with what I don't know, which is 2 pi m over k. I'm looking for time. I have number of oscillations. I don't have mass and I don't have spring constant. Well, what I can do is I can eliminate one of these things by saying m is equal to kx over g. We're going to eliminate through substitution. Plug that into here. Now, really, once again, this is an anti-plug and chugger problem. It basically looks for the people who plug and chug and go, what are you going to do now? I give you nothing. But if you do the appropriate substitutions, you can get an answer. M is kx over g times 1 over k. Those k's cancel, and I'm left with, that's an x right there, a mutant x. This is 2 pi n square root of x over g. I do have x, I do have g, I do have the number of oscillations, so I can find the time. This makes it 2 pi n x is 10 over pi squared, g is 10, and when you start looking at this, you can start seeing the answers starting to just pop out. 10, 10 cancels. I'm left with 2 pi n is 30. Square root of 1 over the square root, or 1 over pi squared square rooted is 1 over pi. 60 seconds. Yes?
When did you get x?
X is given the rest and stretch position, 10 over pi squared. So, it is because I say so. That's what it is.
You just had it in red, I wasn't sure.
Oh, I had it in red and wasn't sure. Oh. I lied. I do know X. I was just reinforcing my whole we're doomed routine. All right, problem one. Problem one I had fun with. Typically, I talk with the students during a normal lecture. In this rushed format, I kind of decided, well, we're going to cover it anyway in the test, so we're going to talk about it right now. It is, you may see it on old problem sets or old problem sets or old tests. And sometimes it's used the title, There's a Hole in My Bucket, Dear Liza, which we all remember from when we were playing the piano in 3rd grade. There's a hole in my bucket, dear Liza, there's a hole in my bucket, the hole. It's old children's, roll with it. There's a hole and water is shooting out of that hole. Now, this length here is 20 meters. The radius of the hole is 1 over square root of pi, and it's circular. I'm looking for the time for the amount of water to come out to be 12 12,000 cubic meters. And it's water, and we're on planet Earth. When this hole is letting water out, we're letting out 12,000 cubic meters. And I would think that this is a valid, it's a valid question to ask. The question is, does the surface of the water in the bucket go down as the water's flowing out? That would add an extra layer of the problem that I'm not willing to teach. So I've said that bucket is infinite volume. Like that water is not coming down. So you can always assume that the level of the water is constant. It's a Bernoulli's equation. Why do you have problems with that? I got an infinite bucket. I can assume spherical cows. Work with me. It's physics. We can do all sorts of strange things. So it's a Bernoulli's equation, P1 plus rho GH1 plus 1/2 rho V1 squared equals P2 plus rho GH2 plus 1/2 rho V2 squared. This problem is similar to the shower curtain problem. The shower curtain problem, you deal with 2 points separated by a sheet of shower curtain. The two points that we're dealing with now, one point is there, actually we'll call it 2, and the other point is here. They're both, one is just inside the hole, the other one is just outside the hole. The thing that I'm going to knock out first is H1 and H2. H1 and H2 are those vertical heights. And H1 is equal to H2. So they go away. They cancel. The next thing that we have to think about is the water on this side has a velocity of V2 going this way. And so the next part, this is where we're going to have to conceptualize it and work it through. But I'm telling you about this problem so we can all figure it out. The water, well, where's the water coming from? It's coming from all different sides. And it's all slowly getting squeezed through that hole, and then it just shoots out at a high velocity. So what we're going to do is we're going to say that the velocity on that side is 0. Technically it is non-zero, but it's small enough where you can assume that it's 0. Compared to if it's like 0.01 meters per second and the other side is 5 meters per second, it's not a significant value to take a look at. So V1 is 0. The next thing that I need to do is write this out. So right now we have something similar to the shower curtain, that the pressure at 1 is equal to the pressure at 2 plus the velocity of the water. Well, what are the pressures P1 and P2? And P1 and P2 is the total pressure at point 1, and P2 is the total pressure at point 2. Pressure at point 2 is atmospheric pressure. It's simply 1.013 times 10 to the 5th newtons per meter squared. Since that's going to kick out in newtons per meter squared, let's keep our pressures like that. Now technically in air, the pressure here is slightly less than the pressure there, but we're dealing with air, and so there isn't that much of a significant difference. Pressure 1, on the other hand, you have the pressure of atmospheric pressure plus rho GH. This particular H is not the height like H1 and H2 is. H is the depth from the surface of the water. I'm going to plug these in as equations, and what you see is P atmosphere plus rho GH equals P atmosphere plus 1/2 rho V squared. And what you get is those atmospheres cancel. And I'm left with rho GH equals 1/2 rho V squared. The density of the material doesn't matter. It cancels. So the square root of 2GH is equal to V, because 2GH is equal to V squared. So that's the velocity of the water. Square root of 2GH. Now I'm looking for the velocity, or I'm sorry, I'm looking for the total volume. Flow is area times time, which is pi r squared times time. The volume is flow, I'm sorry, oh, hold on. What did I do wrong here? What should this be? Flow is not area times time. Flow is what? Area times velocity. So you get that. Now, volume is flow times time. This makes it pi r squared square root of 2GH times time. So volume over pi r squared 2GH is equal to time. So this becomes 12,000 pi. R is 1 over square root of pi squared. That cancels with that. And I'm left with 2 times 10 times 20. 2 times 10 times 20 is 20 times 20. Square root of 20 times 20 is 20. So I'm left with 12,000 divided by 20, or 1,200 divided by 2, or 600 seconds. And so that's the time that it takes. Now, one of the things that I do mention in the other classes, and I'm going to do it right now, and that's the test. The thing about this problem that's really interesting is you can actually solve it by several different ways. The way that I want you to do it in class is with fluids. But what's really interesting about it is, say you had, so there's the water shooting out of the bucket, and you drop a stone from a height of 20 meters. What is the velocity of that stone at the bottom of the 20 meters? Well, you could do it one of 2 different ways. And in the end, it will actually be one of 3 different ways. The first way is with motion. X equals x naught plus v naught t plus 1/2 at squared. and V equals V naught plus AT. You set the origin at the top, you set down as positive. X and V naught, because it's dropped and starts at the origin, are all 0. And you're left with 2x over A is equal to t squared, or square root of 2x over A is equal to t. Well, what's the velocity? The velocity is A times t. That's square root of 2x over A. I'm going to bring the A inside. Should get rid of that. 2xa, which gives me 2 times 20 times 10, or 20 meters per second. Over here, the velocity is square root of 2gh, 2 times 10 times 20, and we get the same answer, 20 meters per second. There's another way that we could do this. We could do this problem with energy. The energy solution is way faster. Energy initial, energy final. Energy initial is all potential, mgh. Energy final is all kinetic, 1/2 mv squared. Masses cancel, 2gh, v squared, square root of 2gh is equal to v. Once again, we end up with the same equation. So the water coming out at the bottom of a 20-meter deep tank comes out at the same velocity that a stone would have if it fell that same height. So it's an interesting observation. As for the layout of the problems, are pretty much straightforward. I mean, the multiple choice. I would say that these two problems are metaphysical certainties. You're going to get one that is an Atwood string, probably not for L2, definitely not for L1. It'll be asking for something else, like the mass of the string, first overtone or frequency, something like that. These I don't know. They could be fluids, they could be oscillation problems. I don't know. Probably how I'm leaning towards is the appetizer will either be a simple pendulum or a spring pendulum, and then do something with that. And then problem one will be you gotta let me be a little bit creative. It'll be either like a buoyancy problem or something to do with the fluids and stuff like that. The other thing, this could be oscillations, what we've seen before, or sound. Half pipe or pipe, since this is a string. I would probably say oscillations, since vibrations and sound technically is done here. So if I had to look at this, I wouldn't even, now that I'm kind of writing the test now, I wouldn't worry about sound except for that guy. On the final, because I'm not doing an Atwood string, I'm doing an Atwood's energy or Atwood's motion, I would say that sound, like for pipes or something, would be fair play on the on that. So that's it. Any questions on the test? Just kind of a little rally speech for test 3. Homework is 10%. If you do, please do the homework. It's just basic exercise. If you do it, it can only help you. If you don't do it, you get hurt. A lot of my making decisions about boosting grades up, some of it is dependent upon the amount of homework that you do. There was one dude who got a C- a couple of years ago. A C minus, and I hate C minuses. My C minus is me going, I don't like you. So you got to do something to upset me. I looked at his grades. He didn't turn in a single problem set. And I'm like, well, there you go. C minus. Have fun with that. So it is important to get that homework done. Get it all done. Get it all done now. If you decided not to do the homework, see the error of your ways. I don't even care if it's late. Get it to me. The next thing is test 1 and test 2. That's 15 and 20. That's 35%. That's only a third of your grade. A third of your semester grade is based on those two tests. Test 3 and the final. Test 3, the final, and the homework is roughly 2/3 of your whole final grade. So by pulling out B's on the third test and the final, those will easily cancel D's and C's in the first two. It's just because it's just more tests. You all have taken the physics test for the second time. You know the situation. You know what's expected of you. So charge into it and let's get this done. The other announcement, both test 3s obviously are posted on Blackboard. Yesterday I posted the two finals, so you can start taking a look at that. All the final reviews are online for YouTube. You can start looking at the spring reviews. And so there's a ton of information out there. Yes?
I know like for a regular test you said it takes about an hour and 15 minutes. What about for the final?
Finals. All right. Anybody who walks in and aces my final, you're going to pass. I take great pride in my finals. The finals will... A test is 25 multiple choice, 1 appetizer, 3 problems, and realistically for a summer you got 2 hours. But during a normal semester they only get an hour 15. The class, majority-wise, for tests 1 and 2 get done at about an hour 15, and I was pleased with that. For the final, it's twice the size. 50 multiple choice, 2 appetizers, 6 problems, and 3 hours for both. So for most of you, it isn't that big of a deal. It's just twice the size. Planning on a decent, if I can get the peak of the class to start turning their finals in at about the 2.5 hour mark, which means that they'd be done at 2:15 and then spend 15 minutes to review and then they walk out at 2.5. That's what I'm going for. Those of you who hold on to your final until the bitter end, not that I'm looking at anyone specifically, you're going to have to pick up the pace just a little bit because you're only going to have 3 hours instead of your customary, you would hope for 4. So it's twice as long. I expect twice the time. But then for an hour 15 to go from hour 15 to 3, for most students, they consider that a luxury. For the people who hold on for 2 hours, they're going to have a little bit of a situation. It is comprehensive. Yes?
Is the multiple choice just pretty much old test?
Yeah. I'm not... Dude, I'm blowing this... I'm getting off this university in about 30 days. So I'm not putting any extra effort in these multiple choice. It's... Thank you. I will say this, that the final, what I do is I take the 3 multiple choice banks, which are about 50 to 75 multiple choice each, and then I put it in a I've got a special final spreadsheet that of the 50 multiple choice given, a third will come from test 1, a third will come from test 2, and a third will come from test 3. An earlier version of it, for some freakish reason, of the 50 multiple choice that it picked, like 40 were from test 2. And people were just like, dude, what was the deal with test 2? They wanted a more balanced performance. Yes?
Will that be kind of like how the problems are, like 2
Yeah, I'm gonna work hard on the balance. And on Friday, we're gonna go over what problems I expect. For a metaphysical certainty, add vectors. Metaphysical certainty, probably 2D motion. Metaphysical certainty, Atwood's machine, probably with energy, because we're doing a lot of 2D motion. So let's just kind of talk about it. Add vectors, 2D motion, Atwood's energy. Because it just makes sense, because 1D motion is, or 2D motion is already in it. Collisions. One thing, I'm really thinking about this. And I gotta figure out. You got rotation, alpha equals 0, because we did alpha not equal to 0 on that. That's 5 problems. I still have to include a problem from test 3, so there may be like a fluid, probably another fluids problem. There's all sorts of fluids problems I can ask. I would put the roulette wheel style Doppler shifts as low for the final, because we'll do this on the test. The mystery is that one. And I don't know, I've been talking to that problem, and that problem's been talking to me, and it wants a rematch. And I'll tell you one of the reasons why. Okay, fine. Let me tell you why. It's because you guys did so badly on it. And one of the things that I do is I look at the performance of, the class did great on right hand rule. That was 5 free points. It was just money falling from the sky. So that won't show up on the final. The conversion won't show up on the final. There are things, the biggest problem that I have is I only have 6 problems, 2 appetizers to cover a whole semester of physics. I have to hit the high notes, the big ones. And so if I do those 5, and I've got 2 appetizers, on fluids and oscillations and sound, and I'm looking for a 6th problem, that rotation problem looks really good. Most likely what I'd want to do, just talking it out loud, because a lot of times when I'm thinking, I'll just say it to the room, and if it sounds dumb, then I'm not going to do it, is I don't find it quite fair to make both appetizers test 3 material. You need one problem for test 3 material, so that may push that to an appetizer with another test 3 type problem. If that happens, then I've got to water down that problem. I got to make it an appetizer problem rather than a full problem. I don't know what I'm going to do. One of the benefits that I have is the final is on a Monday. The final is at noon, not 10 a.m. Remember, we're on a final schedule on that day. So you come here at noon to 3. probably what that means is I'll write the final over the weekend, show up 8 a.m. on Monday and print it, which means that gives me the whole day to just kind of work it out note-wise. I mean, if for 54 finals, it takes about 20 minutes to print. So I'm not hurting for time that day. This is something that I won't throw away. It's something that I'll keep and I'll just use it. I'll hold it in my.
Did you say the right hand rule won't be on there?
Right hand, good point. Right hand rule game won't be on it. But the right hand rule needs to be known. Okay, I'll consider it. It will be duly noted. The thing that if I do anything with the right hand rule, it will be with the torque bar, which you guys, a lot of you guys did really well. I mean, granted, and I'll say it right now, both test 1 and test 2 had 3 or 4 100s on it, perfect scores. There are 2 people in the room who have perfect scores for both test 1 and test 2. I will be grading your test individually. You're not going to get a perfect score again. Just saying. I can handle 99s. I'm perfectly happy giving you 100 or a 99, but I can't handle perfection. It's a life lesson. Deal with it. It's all because there was an individual who made it through 213 completely and then got 100 on both test 1 and test 2 of 214, and then the grader brought it to my attention. And I was like, oh no, this is gonna happen. Just give it to me. I'll deal with this. And so, look, you're gonna get an A anyway. Just endure it. So that's kind of an outline of the final, kind of a rally cry for the test. What we'll do now is go over problems if you want, or we can do anything.
Can we do number 10 on the homework?
10 on problem set 8?
Yes.
Mm-hmm. Uh-oh. When you start cackling at the beginning of the question.
So listen. What if I got problems on Monday? Like, can I take it another day or is this out of the
We're talking about finals rules.
Tuesday.
Question, are you taking 214?
I can't because of
Okay. It's got to be for a darn good reason. The university makes insane, like it does very high restrictions for taking the final at different times. So basically, you have to be either dead, in a coma, and I'll want a note proving you're dead. If you're a hostage on a bus, that's acceptable. But if it's just for your job or something, no.
what about another class?
Another class?
Yeah, another class.
No. It's from now that I'm close to the end of my tenure here. No, screw those classes. This is my class. During finals, is it another official Ole Miss class?
Yeah.
Ole Miss classes are not allowed to conflict with scheduled finals. It's right after, then it doesn't conflict, and then you're showing up for the final. So I'm still not hearing, if you lose a leg, you're going to have to bring the leg. So are we understanding? Now the thing that, if something happens and you miss the final, and it's a valid reason, if it's not a valid reason, then I'm just going to just zero it. If it is a very valid reason, you're going to take the final in July at a much later time. That's to prevent people from going, oh, it's more convenient for me to take the final the next day. And I'm not saying that you would do this, but there are people who get debriefed on what's on the final from people who have already taken it. So it's very it's got to be darn good. Like the chancellor has to walk in and say it's cool in order for me to let that slide. So does that make it clear?
Yes.
Excellent. Yeah.
For the test on Thursday, since you're not telling us exactly what's on column 1, could you just like give us options? You know, like could you like give us columns for the test?
Okay.
So it's not.
What I'm going to do is, since the first motion on the floor is to do problem 10 on problem set 8, we're going to do that first. Then we'll talk about fluids problems. So in number 10, you have this system, 2 strings holding up a mass. The mass is dealing with gravity. The question is, what is the tension in the 2 strings? And the first question that a lot of people have is, what is it doing? Totally valid question to ask during a test. Answer, nothing. It's doing nothing. So if it's doing nothing, this is kind of like a special version of the torque bar. Rather than using torque and then translational equilibrium, we're going to use translational equilibrium twice. Now in torque bars, the translational equilibrium is only vertical. Here, both axes have sums that are 0. Some of the forces in X and Y are both 0. When you've got this mass, label the forces. Down, you've got mg. You've got T1 to the right. And then you have T2 going up and to the left. So breaking T2 down, we need to break it into its component parts. We need to convert this vector from effectively a polar situation to a component. So we have T2y and we have T2x. So it matches using the tip to tail method. Up and to the left. Now if, which it is, this angle is 30, then we know some things. We know that sine of theta is opposite over hypotenuse. So T2y is equal to T2 sine theta. I know that cosine theta is T2x over T2. So T2 cosine theta is T2x. Now T1 is entirely in the x direction. It is a pure x vector. mg is a pure negative y direction vector. So I don't have to break those down. This ends up becoming sum of the forces in x, which is 0, is equal to T1 minus T2x. And 0 equals T2y minus mg. mg is equal to T2y, and T2x is equal to T1. Now T2y is T2 sine theta. I'm not going to think about T1 or the x equation, because with the y forces, I know m, I know g, I know theta, I can get T2 right now. It's a lot like a Sudoku puzzle. You got to look for the weak parts first. So mg over sine theta is equal to T2. So this is 10 times 10 sine of 30, which is 0.5. So 20 or 40 is equal to T2. And so we've solved for one of the forces. Well, now that I have T2, T2x I can solve for. But I don't need it. Well, I do need it to get to T1. Now, T2x, T2 cosine theta is equal to T1. So this makes it 40. Hold on. Cosine 30 is equal to T1. Yes?
T2 be 200 because it's 100 divided by 0.5.
Oh, correct. Reminds me I should still keep using my calculator. I went 10 plus 10 in my brain, not 10 times 10. So 200. Thank you. $200 newtons. It's a mutant in. So if that's 200, we propagate that over here. 200 cosine 30. That means T1 173.2 newtons. So it's a continuation of, it's more of a specialization of the torque bar problem. It's a torque bar problem with no torque. It's just summing up forces in the vertical and the horizontal. It's a good appetizer problem left on its own. Probability of that guy being the appetizer, I would say low. Probably very low. Now to look at what could possibly be on the fluids problem, I would definitely look at problem set 7. I want problem set, or I want the fluid problem to be a, it won't be like this because it's fluid and torque bar is test 2 material. We've covered it. So I want more specialized fluids problem. So I could see those 5 being good appetizer problems. If I beef them up, looking at this, to make it a problem, I would say how long to pass like 1,000 cubic meters. make it a little bit more like 5, or add, if I mixed 5 with 1, then I think it would be a decent problem. The others are good, decent problems too. I would basically just go through problem set 7. And if you understand, because then you understand buoyancy, density, Bernoulli's equation. I have asked in the past, it's kind of faded away. It depends on the moment whether or not I'd want it. Sometimes as an appetizer, I would ask about the shower curtain problem. Under what are the conditions under which the shower curtain moves in what direction and why? It's more, that one is interesting because it's more of a conceptual problem with just a few equations. I hate to be so dull, but problem set 7. I mean, gee, thanks, sir. Just study all the problem set 7, I'm fine. Yeah, then it'd be fine. I don't know. That's the one thing. When it probably around tomorrow afternoon, I'll have thought about it and done it. Yes.
Do you know if we could get practice set 7 back tomorrow?
I will. Hold on. I'll remind her. I'll email the graders and let them know that I need problem set 7 in a bad way by tomorrow morning. It may be, has anyone checked? Because they've been turning in stuff. But problem set 7 was turned in effectively today, this morning. So the graders haven't really picked it up. So I'll let them know to pick it up today for sure and get everything that they have returned by tomorrow. Is what I'll do. What are the fun things that I like? All right, one of the things I'm definitely for you guys is, I know it's summer, so I'm not going to throw just the mean ones at you. If we have a balloon that is tied to the ground and it is filled with rebellium, dang it, this is why I brought the book. It's filled with helium. The tension in the string is 10,000 newtons. The mass of the balloon itself is 300 kilograms. Air is on the outside. What may end up happening, because I dislike, well then let's do it this way. We're on a planet, gravity is standard Earth, so gravity is 10. The air that we're using is 1.5 kilograms per cubic meter. This helium gas that we're using, I don't care about the specific densities if they're accurate. I'll probably end up just giving you the values. The gas on the inside is of a density of, and we'll just call it helium for the moment, is 0.5 kilograms per cubic meter. So the density of the gas on the inside is less than the density of the gas on the outside, which means this thing is going to have a buoyant force up. And there is a tension in the string that is 10,000 newtons down. Question, what's the volume of the balloon? The balloon obviously is fully submerged in the atmosphere. So the volume of displacement is going to be the total volume. I'm not really interested in the radius of the sphere or anything like that. I don't think I'll get cute and ask for geometry problems because this is not geometry class. So the sum of the vertical forces, because this thing is tied down, is 0. That makes it buoyant force up, tension down, mass of the shell, or mass of the balloon times gravity, and then the mass of that helium inside times gravity. The equation that we need for all of this, the Swiss Army knife equation, density, mass divided by volume, or mass is density times volume. So the buoyant force is density of air, volume, gravity, minus tension. The mass of the balloon I do know. The mass of the helium is density of helium times volume times gravity. So you have to set up your forces correctly. The other thing that we do is, I know that the density of air is greater than the density of helium, but it is of approximate value. If the density of air was 1,000 and the density of helium was like 0.01, then you could forget, then you wouldn't have to do this part because it would not give a significant contribution. I'm looking for volume, so I got to put all the volume terms on one side. Density of helium, Vg, minus density of air, Vg, equals, that goes over, that comes over, minus T minus mBg. I'm a little bit bothered by the fact there's so many negatives on this side, but what we're going to find out is that this value will be negative. Vg, density of helium minus density of air, is equal to, I just hate negative signs sticking out, so I'll just factor it. And I get this. So volume is negative T plus mBg over G, density of helium minus density of air. Now you just plug it in. Minus 10,000 plus 300 times 10, 0.5 minus 1.5. Oh, I do love this. 0.5 minus 1.5 is minus 1. That will cancel out with that. And I'm left with 10,000 plus 3,000 divided by 10. So the volume is 10,300 cubic meters. And so that is the answer. The big point of all of this is to get that. If you got that equation set up correctly, then you're good to go for the rest of the problem. Let's see, what else could we do? Okay. You've got a pipe. The height difference is Ooh, we could do, ooh, all right. Oh no, professor's doing his oohs and ahs. That's bad. We've got a pipe with a height differential of 30 meters. At the bottom, oh my goodness, this is awesome. At the bottom, the total volume is 10,000 cubic meters in 100 seconds. So 10,000 cubic meters comes out of that pipe in 100 seconds. The pressure at the bottom is 8 atmospheres. I gotta make the problem decent. The area at the bottom, I'm gonna say is 0.8 square meters. The question that I have is if the area at the top is 0.6 square meters, what is the velocity of water at the top and what is the pressure at the top? This is a good test problem. Because it combines, it uses flow continuity equation, it uses Bernoulli's equation, it has to it requires you to keep track of units. So it's a good, it covers a lot of bases. If I give you volume and the area of the pipe here, you know that volume is flow times time, and flow is area times velocity. We can solve for V2. So volume divided by A2T is equal to V2. So this is 10,000. A2 is 0.8. The time is 100. So that is left with 100 divided by 0.8. And I'm left with an insane velocity of 125 meters per second. Now, the numbers for a dynamically created problem such as this, it most likely will give me a nonsensical answer at the top. And the way that I'm going to compensate this is I'm going to, on the fly, declare not 0.6. I'm going to declare that the area is, oh no, I need to compensate somehow. Let's keep it at 0.6 and let's just roll with it and see what happens. I'm interested to see the numbers. So if the area at the top is 0.6, the area at the bottom is 0.8, we now use the equation of continuity to determine the velocity at the top. A1 V1 is equal to A2 V2. V1 is A2 V2 divided by A1. So that A2 is 0.8. V2 is 125. A1 is 0.6. So this becomes 166.67 meters per second. Now these velocities, just looking at them, are high, but there was one time back in the day, I would just throw problems together and not really care what the numbers were. It was during the time when I was teaching the Cal-based physics course, and the funny thing about it was the water at the top was like 10 meters per second, and the water at the bottom of the pipe was 2/3 the speed of light. And some people were like, are we serious about this number? And I looked at it and I was like, that's an engineering problem. It's not my business to know how they're gonna get water to go up to 2/3 the speed of light. But it did, it was no big deal. But these are realistic numbers. Now that we have the numbers, we're gonna have to give us Bernoulli's equation. P1 plus rho g h1, that h is gonna be 30, plus 1/2 rho v1 squared equals P2 plus rho g h2. H2 is 0, so that's gonna go away, plus 1/2 rho v2 squared. So the pressure at the top is equal to P2 plus 1/2 rho v2 squared minus rho gh minus 1/2 rho v1 squared. So we get that. Question, a legitimate question to ask during the test is, if I don't mention it, ask me, what units do I need P1 to be in? Do you want newtons per meter squared, or do you want atmospheres? As written, that's a very legitimate question. I want atmospheres. Because I ask for atmospheres, you're going to have to convert parts of the equation, but not all. P2 is given in atmospheres, 8. But these three terms will kick out newtons per meter squared. So this gives you, I'm going to do an odd thing, factor out rho, V2 squared over 2 minus GH minus V1 squared over 2. And then this whole thing I divide by 1.013 times 10 to the 5th newtons per meter squared divided by atmosphere. So those things, the units cancel and I'm left with atmospheres. Now we plug and chug, and now we figure out how weird these numbers are. Rho is 1,000. V2 is, what did I say, V2? 125. Oh, goodness. Minus 10 times 30 minus 166.7 squared over 2. And I divide that whole thing by 1.013 times 10 to the 5th. The thing that troubles me is we may end up with a negative number in the numerator. And we will. Oh, wait. It depends on how big that number is. All right. Minus 166.7 squared divided by 2. It's not that bad. All right. Let me do I want to do the math again. Okay, all right. I think we may be good. No, we're not. Oh, we're really off. So the answer I get is aesthetically pleasing. It is negative 55.000. The thing that bothers me the most is that, or the way that I would fix this. One, I promise you that the numbers will look legitimate on Thursday. The reason why the numbers aren't legitimate is that I just made them up. I'll have a spreadsheet all done just so that the numbers work out beautifully. It won't be that bad. Or it won't. It'll be, if it's like this, the numbers will be like, you'll get an answer, P1 will be 2 rather than negative. Granted, a negative pressure is nonsensical, but let's just roll with it. The procedure is exact. Yes.
So just to make it clear, the past 2 columns you've done would be like the actual problem written out on the test, but column set 7 would be good examples for an appetizer.
Answer, yes.
Okay.
In terms of some of the problems, like thinking about the test, the appetizer most likely, I would say with 90% guarantee, is going to be an oscillation. Which means that the problem has to be a full strength fluids problem. Which means that if I pick any of those 5, I'm going to have to beef it up a lot. This, I'm probably just... This one is more of a... this one's a really good multiple choice. As an example, you're 30 meters underneath the water. What's your total pressure?
4 atmospheres.
4 atmospheres. What's the partial pressure due to the water? 3. What's the atmospheric pressure? 1. So you add the 2 and get 4. That's what 8 would most likely be. So I'd pull 8 and make it a multiple choice. So I'm thinking it's either going to be a Bernoulli's equation problem of some sort, most likely like the tube problem. A lot of it depends how I write tests. For 3 problems, I'll write 8. And then I'll start picking out problems and going, oh, this one looks like a misfit, get rid of that. And then it's the 3 problems that make the most sense. For the fluids problem, I'll probably write 3 of them just to see how they work. So it could be a Bernoulli's like we just did. It could be the hole in the bucket like we just did today. It could be a buoyancy problem like we just did like this. Probably change it up a few different ways. If I do make it hybrid, I can't include like test 2 material just because we've already done it. But I think that's it. I've been on a big kick lately about flow. Volume is flow times time. I don't know what that means, but we'll figure it out. You'll know on Thursday. Yes?
Can we do 1 through 5 on problems A?
Okay. 1 through 5 on problem set 8 is me going, we need to know this for the final. This is the problem from the test wanting to go, hey, remember me? You guys need to straighten this out. So this is what we're doing is we're looking head down on a wheel. The wheel has a stick. There's a force at the end of the stick. The first thing I need to do is find the moment of inertia. We have the moment of inertia total is the moment of inertia of the stick plus the moment of inertia of the disc. And this is the moment of inertia of the stick using the parallel axis theorem. because the stick is not rotating about its center of mass, it's rotating about its edge. So this becomes 1/12 ml squared plus m stick d squared plus mass of the disc r squared over 2. So this is 1/12 mass of the stick, 75, length of the stick, 10, mass of the stick, 75. D in this case is the distance from the middle of the stick, the center of mass of the stick, to the rotation point. So what value do I use for D? What's the distance from the center of mass, which is here, to this rotation point? And we're going to stay here until someone says it. Because you should know this. It should be, there should be a tone of insolence in your voice when you answer this.
L/2.
It's L/2. Excellent. You could go a little bit more insolent. L/2, since it's 10, divide by 2 to get 5. Mass of the disc, 120. Radius is 5. 5 squared divided by 2. And that gives me 4,000. Now I need to know alpha. Sum of the torques is equal to I alpha. We have one force, one torque. The force is F. Now torque is force times that distance, little d, the lever arm. The distance from the rotation point to the force itself, which in this case is L. So alpha is FL over I, 210, oh, these numbers are working nice, 4,000, so this is 0.5 radians per second per second. Now, what I'm going to do briefly, I'm going to skip to 4 because I'm going to knock out torque. Torque is, sum of the torques is I alpha, which is equal to force times that distance. So you could write 200 times 10 or 2,000 Newton meters, and that's the torque. So now 4 is answered. So now let's go for 3. For 3, it's theta equals theta naught plus omega naught t plus 1/2 alpha t squared. Those are 0, it's always 0. Theta 2 pi n 1/2 alpha t squared. So n is 1 over 4 pi alpha t squared. So this becomes 0.5 divided by 4 pi 60 squared. And that gives us 143.2 times. The last part, the omega, is omega equals omega naught plus alpha t. Omega naught is 0, alpha is 0.5, t is 60, so omega is 30 radians per second at time equals 60 seconds. So it just uses summing up moments of inertia, parallel axis theory a little bit, then understanding that the sum of the torques is equal to I alpha. The thing that you have to be careful is that torque is not always force times the radius of the disc. It's true meaning is force times the lever arm length. So the lever arm length frequently is R, but sometimes it's L, and sometimes it's L over 2, like it was in the test. If it was the test, then you would substitute L with L over 2, and then just run with it. Okay. So, because it's a homework due day, tutors will be in the tutoring room starting at 1. I've got my normal office hours. This will be online shortly, and that's it.